Could someone please start the Google Hangout on their laptop? I just want to make sure the audio is working. So it'll sound bad for a second. Hey there, we're getting started here. We want to make sure the audio works. Is everybody diligently starting? Are you starting it? I should just have one person. You start the Hangout, please. I sent email.
So you sent the link in the email?
Huh?
You sent the link
Via T-Square. Hi, I see we have 8 viewers. Hello. Unfortunately, the Q&A function isn't working right now, so please post questions you have on Piazza. I put a note up on Piazza, which is post your questions here. So go ahead and post questions there and I'll answer them. But we're waiting for just a moment to make sure the audio is working. Yeah, there's a lag. Do you have your sound on? Okay. Waiting for just a moment to make sure. All right, cool. Okay, so I'm going to talk about decision trees, and I'm going to use this. Does anybody know what this is? No? Who knows what it is? Well,
Pokemon.
Huh?
Pokemon.
No, well, it looks like a Pokemon. Let me turn on the sound in here. Let's see. So this is it's an amazing thing. It costs only 20 bucks and it's packed full of all kinds of AI. It's got decision trees, it's got speech recognition and speech generation. Some of you kind of look doubtful, like you don't believe all that, but it's true. Okay, so what this thing does, did you ever play 20 questions?
Yes.
Maybe it's an American thing. Yes, okay. All right, this thing can figure out which animal you're thinking of by asking you a series of questions. So we're going to kick it off by randomly selecting an animal. Marshall, I'll allow you to choose one piece of paper.
That one.
Okay. I don't want to show this thing. Does everybody see what that is? Okay. All right. Here, I'll show it. Here's the animal that we've got. Oh, it's weirdly backwards. Okay. Anyways. All right. So let's try it out.
Hey there, buddy. Want to play? Great! I love guessing games, especially when I'm sure to win. Think of an animal. Say, okay, when you're ready.
Here's the voice recognition part.
I didn't understand. Say it again.
Okay.
Nice. I'm going to ask you a question. Answer yes, no, or I don't know. You can also say, it depends.
Okay.
Can it swim?
No.
Very interesting.
We should probably have a volunteer up here to help me
Does
with
it
this.
have hair or fur?
Yes.
Aha, I see. Does this animal have a long tail?
I don't know.
All right. Does it have claws?
No.
Does this animal have hooves?
Yes.
That's what I thought. That's it. I've read your mind. But I'm going to ask you a few more questions just for fun. Does it have horns or antlers?
Yes.
All right. Is this animal very big?
Yes.
Okay. Does this animal live on the savannah?
Yes. I think he's going to get us.
Very interesting. Is it dangerous to humans?
I don't know.
Aha! I see. Does it have spots?
Yes.
I know. Don't tell me. I have a feeling that you were thinking of a giraffe. So, am I right?
Yes.
Unbelievable! I'm so proud of myself. One more round. See you soon, friend.
Okay. It's a little bit creepy, but yes.
What's the database of animals does it have? Like, what's from?
I don't know. I know it doesn't have skunk. It always, whenever I try to have it do skunk, it comes up with polecat, which is not exactly a skunk. But it has parrot, it has porcupine, it has narwhal, you know, the whale that has a thing. I think it even has, mythical animals as well.
Does it ask the same kind of questions, or it depends upon your answer?
No, if you, in fact, if we were to run it again, it starts with different questions.
So it's basically maximizing entropy at every step, depending upon your answer.
I believe so. You know, I brought this forward as an example of something using decision trees. To be honest, I don't know for sure that it's using decision trees, but decision tree would be a good way to, you know, to create this. But yeah, and in fact, that's so for those who couldn't hear him, he was asking. So at each question, it's trying to maximize entropy, or it's prioritizing questions that divide, you know, all the possibilities into the largest or most differentiable group. And you will notice that, you know, at first it asks broader questions like, does it have fur? and then it starts getting more detailed, like does it have horns and spots and stuff like that. And yeah, so as it moves into smaller and smaller potential groups, presumably it finds questions that divides those groups most efficiently. Yeah.
One question you asked was, can the animals swim? And we answered no. I'm not sure if that's the right answer. So if suppose a giraffe could swim, and we said no, how do you suppose it kind of corrects itself?
So I've done, let me answer for people online, or repeat the question. The person asked, the thing asked, can the animal swim? And we said no, and maybe it can. And how does it adjust, if you essentially steer it the wrong way? I have noticed that if I give it a wrong answer, it doesn't recover. It ends up getting kind of lost. It doesn't know what to say. Eventually, it'll say, "Oh, you beat me." I've seen that occur. I've also I only recently noticed that it would allow you to say, "I don't know," and it's able to deal well with "I don't knows." Yeah.
That could be possible because it might be using the hard decisions to kind of eliminate things. So if you include a soft decision, if you basically let him make soft decisions, then probably it won't eliminate. Even if you say one incorrect instance, then it won't probably eliminate it. Just give a little lower.
Right. So yeah, another potential approach for this, it still ends up being like a decision tree, but you might start with all of the animals being possible and just consider questions that eliminate the largest number of animals at any one point in time, and you just sort of think of it sort of like sets. You just eliminate the largest ones, but that ends up being analogous. I think essentially equivalent to decision trees. But anyways, so let me pause for a second and see if anybody online has a question. Remember, again, post your questions to Piazza. I'm sorry, the Q&A thing isn't working right now. So to give an overview, I'm going to spend a few minutes here at the beginning talking about decision trees, and then we'll shift modes into Q&A, specifically to focus on the assignment that's due Monday. But of course, I'll answer other questions as well. Let's see. People say the sound is good. Thanks. Not a question, but that toy sounds a lot like Mark Hamill. Terrifying. Okay, yes. I'll tell you something that was weird about this. I was carrying it around in my briefcase, and somehow the nose button got pushed, and so I was on the elevator, and it was like talking and stuff. And it was really embarrassing. People were looking at me like, "What the hell is that?" Anyways.
See you later.
All right. I might want to give that toy as a holiday gift. What is it called? It's called the Magic Gin, Jinn, and it's made by Hasbro. Okay, those are all the questions we have so far. Okay, let's talk now about decision trees. Decision trees used to be part of this class, and people would have to implement decision trees. I know some people perking up here. Anyways, you don't have to implement decision trees this semester, okay? So don't freak out. But they're really cool, and I may add it back in next time. The reason we're not doing decision trees this time is because we're going to do reinforcement learning. So I added reinforcement learning and dropped decision trees. but I'm still going to lecture on them because they're cool and you might benefit from them. So this is a, you can think of it as sort of like a free bonus lecture. Okay, I'm going to start writing on the board. Okay, so the way I want to start this is, suppose you have a decision tree, how might you use it? So we'll consider this in the context of price forecasting. The way decision trees work is there's always a root node, and each node represents a binary question. So in the case of this toy, there are questions like, does it have fur? Now, we can say yes, no, or maybe. So yes, internally, actually, there's not a requirement that it be a binary question. You can you could have potentially 3 or more outcomes for each node, but it's it's typically easier to work with just 2. So what's in each node is we record what feature are we asking the question about. So let's say we're asking about feature 2. And then you also have to record what I call the split value. In other words, we're looking at feature 2, and if feature 2 is less than 5, we go one way. If it's greater than or equal to 5, we go the other way. So that 5 is the split value. So let's use another color. Feature and split val. So let's say we'll use 5.0. So this represents a question: is feature 2 less than or equal to 5? So if yes, we go that, not less than or equal, less than. If it's greater than or equal, we go down here. Then we've got another node. Everybody following me so far? Okay. Oops. So we have another feature here. Let's say it's feature 1 and split val 2.0. And for this one, one thing that's important to remember is you can repeat features. At each level, you might ask another question about a feature you've already asked about. So we can repeat features. We can also entirely skip features. Sometimes particular features don't matter at all, and the algorithm used to learn the decision tree essentially infers this and chooses not to include that feature in the tree. But okay, let's say over here, we repeat that feature, say feature 2, and so if we come down here, it's got to be greater than or equal to 5. So let's say here we split on 7.5. And I'll do one more level. Just randomly pick some features here. And we'll say, I'm just making these numbers up here. Okay, these are all leaves, and down the bottom. And so when we go through our series of questions, what? That was cool. When you get to a leaf, boom, that's your answer. So let's try an experiment. Let's suppose our query, so we have 3 features that we're considering here. Let's suppose our values are 0.5, 7, 0.0, and 10. What is the result of that query of this decision tree? Let me get the camera closer for our online friends. Raise your hand if you think you know the answer. Let's see, who wants me to show you how to find the answer? Okay, all I can do then is sit and wait. Huh?
I want to know how to find the answer.
Okay, all right. Thank you. Okay, someone wants to know, so I'll explain. All right, okay. Okay, these are the values for our query. We start at the root node, and the root node says, hey, we're interested in feature 2. Is feature 2 less than or greater than or equal to 5.0? Greater than. So we come down this way. We ask, because it's 7, right? This node, again, asks about feature 2. And the question is it less than 7.5? Yes, it is less than 7.5. Now we ask about feature 3, which has a value of 10. Is feature 3 less than 4.0? No, it's greater than. So boom, our answer is 6. Let's try it, yeah.
Can you have several branches ending in the same leaf?
So the question is, can we have several branches ending in the same leaf? So, so this does not happen. However, it is possible that we might, so in other words, it's possible that we might have a repeated value down here, but it's a distinct leaf. Okay, let's do another one. And I'm gonna pick somebody. I'm not gonna tell you who, but I'm gonna pick somebody to tell us the answer. Okay. So pay attention, everybody. Okay. 3, 3, 3. Okay. Who does not want me to pick them? Good.
So it's 3, the second one, so when you go to the left, it's less.
Okay. Let's use another color. Okay.
And then with the first one, which is 3, so it's 20. So it's going to go to the left.
That's 2.
Oh, it's 2. Sorry, so it's near the right. And then we're at a 3, so it depends which way you set it up. It's gonna go.
So greater than or equal to.
Okay, so it's to the right.
Da, 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 da. Okay. All right. So does everybody get how decision? If you have a decision tree, how it works? Now, one thing to point out is right now we're using it like regression with numbers down here at the bottom, but it could be classification like that little gin thing. You know, it could be giraffe and cow or, you know, whatever. However, we're doing regression, so we've got numbers down there at the bottom. Let's see if we got any online questions here. Okay. So the question is, how do you decide what these split values ought to be? And that's a perfect segue into the next part of the lecture, which is, so remember, this first part was, given that you have a decision tree, how do you use it? Next part of the lecture is, how do you build a decision tree? Anyways, that's what we'll do now. Let me move this back a little bit. I'm going to teach, I'm going to show you 2 ways to build a decision tree. It's kind of weird. Let's see. All right. Okay, so this is data just like the data we've been working on so far in the class. We've got a 3-dimensional X. Is that showing me? Yes, okay. 3-dimensional X and a Y. And the first question is, what feature are we going to use to establish our root node? So let me ask you, how do you think we should go about deciding which is the best feature to use? Raise your hand if you think you have a good idea. Yeah.
So the feature that divides the data set into close to equal halves or has the maximum entropy should be the first feature that should segment the data. Okay, so
his answer is the feature that has the maximum entropy. Describe that a little bit more, what you mean by maximum.
That means that that feature has, so let's just suppose if x3 is that feature, that means for half of the values of x3, y is, so if y is a binary classification model, then for half of values of x3, y is 0, and half of values of x3, y is 1. So basically it divides the data into 2 parts. Okay, so his response was it's the feature that best divides the data into 2 parts, right? Is that kind of what you're saying? for
Okay.
primary classification.
Okay, and right, that's for classification problems. I'll say it's a little bit easier to do this with classification problems. Now, assume it's a regression problem. You're headed in the right direction, but what other method could we use for comparing these different features and measuring which one might be the best?
So in a similar way, the data divides half of the labels into basically below the mean, half the labels above the mean. Then possibly.
Okay. No. But I don't. Sorry, I don't mean to be a jerk. Anyways, yeah. Go ahead.
So, sir, you look at the information gain for each of the features, and within each of the features, I have suppose list of values. So for every value, I try to split and find the information gain. So I keep a track for one particular feature, the information gain for every split point, and then keep a track of the best one over there. Do the same for every feature. So take the highest information gain, which and the best split point.
So his answer is about information gain. How do you measure? And you might be right. I need to think more about your answer, but there's an easier answer. Okay. Anyways, how do you measure information gain?
So yeah, this time what he said, the information gain when you calculate a particular point, we see if I take this point and I say that everything that comes greater than this point, I put it up on the left side, and whatever comes less than this on the right side, or vice versa. Whatever.
So you would.
So you see how that point is dividing the data set.
So you choose. You're saying you choose a feature, and then you choose a split value, and see how well that split value divides the data. Okay, but I still don't know why it is that you're choosing that particular feature.
No, so you do this thing for every feature, and then you pick the feature which has the highest information gain, and within that the best fit one.
Okay, all right.
Yeah, so you're double. So you're keeping.
So let me let me jump to one answer. Okay, who was the anyways, it's a really famous paper where decision trees were first described. It's by a guy at Ames Research Center, and unfortunately I can't remember his name. But anyways, this is the method he suggested, and it's the following: you take the correlation between x1 and xy and measure it. Correlation between x2 and y and x3 and y. And the one that has the highest correlation is the one that you use. So that provides a measure of information. Does everybody follow that? Now for our data, for real stock data, these numbers are going to be really, really low, the correlation. But anyways, so we look at the correlation between each feature and why. That tells us which feature to split on. So that solves. Let's see, where's my eraser? So that tells us the answer to the feature. Let's suppose that's feature 1. How do we choose now what the split val ought to be? So we know now we're going to use this feature. Which value of that feature should we split the data on? I'll give you a hint. We want to, as much as possible, to build balanced binary trees.
The median.
Marshall gets the bonus point. The answer is the median. Here's what you do. So why the median? Because the median is by definition the number that divides the data in half. So here's the I'll try and note the steps here. So we select the feature by correlation. So that tells us which one we're going to use. Then we sort the entire array by that feature. So in other words, we look at this feature only, but we rearrange all these rows so that after they're rearranged, this column is in sorted order. Does everybody buy that? Everybody get that? Then you find the value in the middle. Now, listen very, very carefully. This next part is really tricky, okay? You divide the whole table in half. Let's see. All of these values are less than the median. All these values are greater than or equal to the median, right? So I'm just going to write median here for the split value. Then what we do is we take this chunk of data and we build the left-hand tree, and we take this chunk of data and we build the right-hand tree using exactly these steps. And that's it. It's pretty awesome, isn't it? Well, there's one part missing. What did I miss?
So I just had a different question. So by doing this process, are we assuming that the features are independent of each other?
No, but I don't believe it matters if they are dependent. There's always going to be one, even if it's just noise. There's going to be one that's a little bit more correlated with Y than the others. Yes.
So in this case, for the leaves, we're gonna have one row of the
You got me. That's what I left out. How do you make the leaves? So you continue this dividing process. Split on median unless only one row And let's suppose it's this row. And let's say this is that leaf. What's the value of the leaf? Where over on this part of the board would I extract the value that should be the leaf? I heard somebody speak. Raise your hand. Be bold. Bold colors, not pastels. Come on. Yes.
So this is essentially like a divide and conquer. So
Say it again.
this is essentially like a divide and conquer. So when you do a divide and conquer, you basically look at the value, the final median value that you have. You don't, it's going to be a set of one value itself.
So let me roll it back a little bit. Okay, it is divide and conquer exactly. So for our first divide, we had this data and that data. This data we used to build this side of the tree. And internally, this is a tree just like the big tree. It's generated exactly the same, has the same semantics and so on. We use this data to build that side of the tree. And we keep each time finding the best feature and dividing. So maybe this time on this side, 2 is the best feature, and maybe on this one, 3 is the best feature. But we divide again, and this data here is then used to build this tree or subtree, and this data is then used to build this subtree, and you keep dividing down. Eventually, though, when you divide, let's say we're dividing up here, eventually when you divide, you end up having just one row of data. When you have just one row of data, that means it's a leaf, because you've asked all the questions you can, and now we're at a leaf. But the question is, what is the value that goes in that leaf when we're looking at that last row?
Why?
Woo! Yes. Sorry. The answer is y. This value right here. What else can it be? Well, it can't be anything else. So, anyways, you're exactly right. Okay, let me pause for a second and just see if everybody. It's extraordinarily easy. Well, I should say, it's one of those things that once you get it, that's easy. But if you don't get it, it can be a little bit hard. So, does anybody have any questions about how this works? Yeah.
So using leaves, you're always going to have an answer to your feature values that is going to be contained in the white data. So
Ask that again.
we're always going to end up in a leaf that is a value of the white column.
Yes, the only, I think what you're saying is the only possible values for the leaves are exactly.
Yeah, so it's a discrete set. How this is better than, I know it depends on the type of data and everything.
Mm-hmm.
You have to have a very dense data set for this to be like useful.
Yes, so let me, I'll repeat her question. So she had a point and then a question. So the point is, only these Y's can be leaves. So each leaf must be exactly some particular value in Y. And so her question is, in order for that to be useful, this data has to be very dense. or well, that's what you said. And so how can this be useful? Yeah, I think that's a fair question. Now, it's going to take me about 5 or 10 more minutes to answer your question, because there's a couple more steps. But something to point out, just one second, is there's a name for the kind of tree that comes out of this, and it's called a perfect tree. What a perfect tree means is if you go back and query, so you build this tree, and then you query on the data that you use to train it. So an in-sample test, it will perfectly reproduce the data. So it's a lot like KNN with K equal to 1. But note, and this is one way that it's useful, we can query this much more quickly than we can query KNN, right? Because I always get my powers of 2 messed up, but let's say we have 1,000 data elements. We only need to ask and answer 8 questions to query a tree with 1,000 leaves, or 1,000 data points that we trained it on, right? Is it 8? Anyways, so asking 8 questions is much faster than measuring distance between your query and all, measuring the distance between your query and all 1,000 points, and then sorting, and then finding the smallest ones and so on. Just answering 8 binary questions is a lot faster. So if the algorithm you've got to start with is KNN with K equal to 1, this one is better because it's a lot faster at query time. It does have the weakness, and remember, we should always be thinking about train time versus query time. It has the disadvantage that this training operation is expensive. Let me see if we have any online questions, and then I've got more stuff to say. Somebody online correctly answered my earlier question. Good job. Shout out to Matthew. There's 2 Matthews. Okay. Is a feature excluded if it is never the chosen feature from correlation? Let me restate that question. So each time here we split the data in 2 and we do correlation to find out which feature to use. We choose a feature, and he's saying, well, what if it never gets used? Well, if it's never used, that is a good indication that it's not a useful feature. So the answer would be yes. That's something you can do, is choose to exclude that feature. Okay, so this is how to make a perfect tree. Let me think for a moment. Do you all think this method is subject to overfitting?
Yeah, actually, that's what my question was, because if you're giving the perfect labels, that means when giving the test also, it will give the same kind of labels that will be more prone to overfitting. Right, yeah. So
it's prone to overfitting in the same sense that k nearest neighbor with k equals 1 is overfit. Usually when you describe overfitting, it's with respect to something that you're changing. I'm not sure exactly what we would, here's the kind of thing that we can change to reduce overfitting. Easy thing. Instead of stopping when there's one row, what if we stop when there's, well, let me make sure everybody knows where we are. We're splitting up the data. Each split, we go down in a subtree. And so far, our algorithm is when we finally split and there's only one row left, boom, that's our leaf. What if instead we say 3 rows? So let me ask, let's suppose these are the 3, I'm running out of, it's hard to see what I'm talking about. Let's suppose these are the 3 rows that we end up with. What value should we put in the leaf in that case? The mean of these 3 lines. Now suddenly we are less susceptible to overfitting, right? And if we wanted to measure, overfitting, this is a lot like K, right? We can vary how many elements we squish into the bottom value, and we could measure overfitting with that. And it's still going to be faster than KNN. So let me mention a couple other nice things about decision trees. It's often the case that we are missing data, like for a particular stock, maybe we just don't have the PE ratio. Maybe for another stock we don't have the PE ratio. Well, decision trees can handle that without any problem. All that occurs is if you end up having some number of nans in your data, you can split. You have to write a little bit of additional code, but you can split on is it nan or not. And if it's nan, you go down this path, and now this model, this subtree, you can think of it as its own model. It's a model of all the data for which we don't have PE ratio. And it's trivial to make it work. You can never do this with linear regression. Okay. So this, all right, so I've showed you if you have a decision tree, how can you use it? I also showed you how you can build a decision tree. And I've told you about some of the good things about decision trees. There's a little bit more I want to say, but I'll answer your question.
You said you can't do that with linear regression. Can't you define an error code, say like -999, and then have a dummy variable, say that observation use that existing criteria? So I think linear regression can handle it in that sense.
He was suggesting a way to handle, in linear regression, how to handle nans. There are, the best way I've seen for handling nans in linear regression is let's suppose it's a few nans in X3. What you can do is take the mean of that column X3 of all the values that are not nan, and then plug that into where the nan is. So it ends up being just kind of, the aim is to make it sort of a neutral value that doesn't cause too much of a problem. You could also have a special case if it's nan. I mean, you could in linear regression build 4 models. One linear model if you've got all 3, one linear model if one of them's nan, another, and just do some if statements to go through them. But, that's what decision trees solve for you. Okay, so here, what else can we do with decision trees? Well, we can bag them, just like we can do with KNN and linear regression. So we can take our data, grab a random sample of it, boom, train a tree, grab another random sample, train another tree, grab another random sample, train another tree. You see you get the idea there, right? Guess what the name for that is? Random forest. That's right. Anyways, it's a forest because there's lots of trees, and it's random because we're grabbing random bags of data to train it. And then, let's say in one tree, you just query all your trees, take the mean of the answer, and that's your answer from the random forest. One other thing to say, well, there's lots. Random forests are cool. One other point, though, that's really interesting is it does take a long time to build one of these trees, because at each step you're running correlation on each feature, and then you're sorting, and that's expensive. There was so the sort of father of decision trees was a guy named Brayman. He was at UC Berkeley, and I don't know if that's how you pronounce his name, but he's dead now. So, anyways, that was kind of mean. Okay, anyways, nobody will know is all I'm trying to say. Anyways, he had a brilliant woman student, and what was her name? Let me look up her name. Just a second. Adele Cutler. So she was his PhD student, and she discovered the following, which is really cool. She discovered forget this. Doesn't matter what the correlation is, just pick a feature at random. So that eliminates all this cost of doing the correlation, right? Next thing was, she said, screw this. She probably didn't say it exactly like that, but anyways, let's not sort either. Let's just pick 2 values at random and take their mean, and that will be our split value. So she took the 2 most costly components of tree building out of tree building, and instead essentially just picked random feature, nearly random split val. Let me repeat how the random split val works. Okay, let's say we've decided we're going to split on feature 2. You then, in this column, randomly choose 2 of those values and take their mean. Now, that has the negative result that our trees are not guaranteed to be balanced anymore because we're not sort of splitting them in half. But it has the positive consequence that it's really, really fast. Anyways, she discovered that if you follow her method for building trees, the quality of the result is just as good as this very deliberative method for building trees. Furthermore, the individual trees, so one thing you're looking for when you're building ensemble learners is that the different learners are uncorrelated. So if you're using exactly the same methodology for selecting features on each tree, your trees are more likely to be correlated. So she discovered that if we throw out those aspects, each of our trees is less correlated, and in some cases, the result of these random, totally random trees is actually better than the original deliberative way of building decision trees. What's going on over here? Just people going out? Okay. All right, so that's what I wanted to talk about with regard to decision trees and random forests. Let me take questions now about decision trees and random forests. Yeah.
So what kind of data does a decision tree not do such a good performance?
So what is so the question is hold on, let me just want to see if we have any questions here. Hold on. There we go. So the question is, what sort of data are decision trees not good for? That's a great question. My experience is that for any data that KNN is good for, decision trees are also good for, and in fact, sometimes better. In fact, I saw recently that at least some group of people consider the sort of best out-of-the-box learning algorithm is decision forests with bagging and boosting. The decision trees themselves are somewhat resistant to overfitting, especially if we put a lot of values into leaves. Bagging makes everything better. So the sort of default out of the box good learner is decision trees. Here's the kind of data that any particular learner might be bad at. Okay, so if it would not be as good as linear regression for problems that are linear. It would not be as good at a polynomial problem if the problem is polynomial. So if we know those things about our problems, we can sort of take the bias of the learner, to take advantage of that. Decision trees are fairly unbiased. See if we have any other online questions. No more. Okay. A couple other things you can do with decision trees that are interesting. Remember, I said instead of waiting until we have just one row left and letting that be the leaf, this could be 3. It could be even larger, maybe 100. And then instead of taking the mean and sticking it in here, we could create a linear model and stick it in here. So now, some set of beta values. We follow this set of questions till we get to the leaf, and then we query our linear model to see what the answer is. And those, and remember, linear regression is really fast at query time. And let's suppose you, let me just give you an example. Let's suppose we had a problem where the data, I know this might be hard to see online. Let's say the data looks kind of like this. So it's clearly nonlinear, but if all we did was figure out G, let's split it into these three groups. And then build a model here, and maybe the other one there. We've essentially, we only need to ask 2 questions to get down to these linear models. And so we can very rapidly build essentially piecewise linear models using decision trees. And you don't even need to really, usually when you say piecewise linear models, you got to think carefully about where you split up the data and how you draw the lines. It's just trivial for it's trivial when you build these decision trees. It just happens automatically in the right spot. Okay, that's all I have to say about decision trees and random forests. Does anybody have any questions on that? I want to shift now into questions about the project that's due Monday, unless anybody's got questions about this. Yeah.
What are the good strategies to generate the data so that linear regression performs better than KNN?
Okay, say that again. I'm sorry, I was.
So one of the questions is, if you generate a data set, a sample data set, where the linear regression model will definitely work better than the KNN learner.
Right.
What are some good strategies to do that? What are some of the properties that we need to keep in mind?
So the question is, what's a good strategy for solving the first question, which is generate data that linear regression is able to solve well, but KNN is not able to solve well. Here's a way to approach it. Write down the strengths and weaknesses of each type of learner. Especially consider the weaknesses. An obvious one is an obvious strength for linear regression in terms of the quality of the error and correlation is if the data is linear, it solves that pretty well. What are weaknesses of linear regression? If the data is not linear, it's a problem. Similarly, think about what are the strengths and weaknesses of KNN. And an important thing, when I look on Piazza, everybody's got set in their head K equals 3. Like that's the only value that K can ever be. I would encourage you to think about other values of K. Now, K equal to the number of data points is maybe a little bit excessive, but think about other weaknesses of KNN. Yeah?
For the second question, or generating data performs better with KNN linear regression, does it need to outperform for both in-sample and out-sample?
So the question is, for the second one, where we want the data to work better with KNN than linear regression, should it work better both in sample and out of sample? So that brings up a point I want to make. Based on some of the questions I've seen on Piazza, I think some people are doing the following. Okay, and I didn't anticipate that they would do this, and I think you shouldn't do it. But let me state what it is. So they've got their 60% in sample, and let's say they've got that data looks kind of like this. So this is the case where we're trying to make KNN good and linear regression bad. Let's see, let me think about this for a moment. Make sure I have this correct. Okay. So they've got a few data points over here. Now, can you guess what their out of sample data looks like? It looks like this. So poor old linear regression says, look at this data. It's so nice and linear. And my model looks like this. So then when it comes time to do out of sample, linear regression gets hosed, right? KNN does not get hosed because there's a few little breadcrumb points over here. Okay, so it is possible to create a data set, especially in the second case, where KNN does better and linear regression does poorly, without, I call this sort of like loading the test set. This, having completely, essentially creating your data differently for the 40% than the 60%. You should create your data, you should draw it from the same distribution for the first 60% and the second 40%. You can accomplish both challenges without making your out of sample and in sample different. It should, and this one, this is the answer to the second problem, right? Just make something shaped like this. Sorry I gave it away, but you don't need to, you can have your in sample and out of sample both distributed, in this way. This will hose linear regression. Yeah.
Wouldn't it basically invalidate the hypothesis behind machine learning that both the in sample and out of sample data should come from the same distribution?
So I'm asserting for this problem that the in sample and out of sample should come from the same distribution. And you're saying that violates something?
The method that you described earlier.
Oh, yes, it does violate that. So, yes, so the statement in the audience is, doesn't creating the data I initially drew there violate the assumption that in sample and out of sample are drawn from the same distribution? Yes, doing it that way violates that assumption.
And also my second question is, doesn't it unfair to just fit linear regression versus KNN? Shouldn't we be also checking it against kernel regression as well? So basically what I'm trying to say is we want to measure performance with KNN with respect to both linear and kernel regression. So what I mean to say is we might be able to fit a higher degree polynomial to that.
So you're saying, well, still though, in the answer to the first problem, you should be able to find situations where linear regression is better than KNN. So his question was, isn't it unfair to pit the fantastic k-nearest neighbor against the pitiful low-life linear regression, right? There really are places where linear regression is better. You know, it's when it's linear. But and by the way, if you choose your features carefully, you are to some extent linearizing the problem. For instance, so if your features are very nonlinear, you can end up turning a nonlinear problem into a linear problem by way of your features.
That would be called kernelizing.
Huh?
That would be called kernelizing, not.
Well, there's different. Kernelizing is one way. There's other, there's other methods that aren't. I wouldn't call kernelizing, but yes, kernelizing is one way of doing that. Okay, let's see online if we have any questions. The question is, does it matter which graphical tools we use to explain our results in the report? Are we limited to Matplotlib, or can we use other tools? Okay, here's, so I've deliberately made this project underspecified. And I know that causes some people some anxiety, because up until now, it's been like, match these numbers exactly, right? So you know exactly what criteria are. I am deliberately removing some of that scaffolding to give you some freedom to be creative and so on. But in general, here is the kind of thing I'm looking for in this report, or what I imagine would be ideal. Okay, I've come up with some great data that I think is going to screw KNN. Okay, it would be nice to see a picture of that data, so I could intuitively understand, what is, how it's going to defeat KNN. So I would plot the points. I don't specifically require, plot the data, but I think just showing what the data looks like is good. And I would show the in sample and out of sample, maybe color them with different dots, so that I could know that they're both drawn from the same distribution. So that's kind of part one. Show me the data. Tell me a story. Why is it, explain in words, why is it that this is really good for linear regression, but it causes problems for k-nearest neighbor? Then numbers, apply the learners, calculate error and correlation. And maybe, maybe your method of creating data just annihilates KNN no matter what K is. So plot error versus K and show me that your clever method, is able to defeat KNN no matter what K is. Maybe bagging helps. Maybe it doesn't. Maybe you should try different numbers of bags. I know that's a wide, huge space of things to try. And I'm not saying you need to try all of them, but I want to see some creativity on your part. I want you to convince me why this data set's better than another, or why this learner is better than another. Anyways, with regard to which graphical tools, no, you're not limited to Matplotlib. You can use MATLAB or whatever visualization tools you like. I do require that your data set generator be written in Python, and that your learners be written in Python. But one thing to mention, by the way, is it's okay with me also if you grab some data off the web, like, you know, frequency of bovine warts, you know, in different regions of the country. That's fine. In that case, you know, of course, you wouldn't have the Python code generator. I think it's a little bit easier to you know, generate, you know, write the code than to find a data set. But anyways, okay. Any other questions? Let's see if we have one online. It's clear how error gives a level of accuracy. It is also clear that correlation is. Can you expand on when you would use error versus correlation? Okay, so the question is, and I'll wrap up. I know that I'm running a little bit long. The question is, when is error a good metric, and when is correlation a good metric? So something to mention about error is it's only useful when you're comparing several methods on the same data set. So it's easy to create a data set where error is going to be huge. Like if the data is, you know, all the values are around 1 million, and like sometimes it's 999,000, sometimes it's 1,000,001. You know, it's kind of teetering around here. Well, I'm sorry. In that case, you might have small error. But if the value is around 1 million and it's jumping, you know, plus and minus 50,000, you could have an error of 50,000, but overall, that's a small percentage of the error. So what I'm trying to say is, let's suppose you've got a learner that's working on one set of data and your error is 0.05. You can't go to your friend who's working on totally different data who's got an error of 50,000 and say, my learner is so much better than yours. It's not because of the learner, it's because of the data. But within the same data set, comparing error is valid. I think in nearly all cases, correlation is a good metric. I'm sure there are cases where correlation might mislead you, but I need to think about that. I don't know offhand of an instance where correlation is not a good metric. I think it's almost always a good metric. Okay, any other questions? I'll look on Piazza and answer them, but that's it for today, and see you all next time in TV land.